Hello everyone, we've got an important variable acceleration question here today. So it's question 8 of a paper, and as you can see it's worth 10 marks, so that's a really good amount of marks. A particle p moves along the x-axis at time t seconds where t is greater than or equal to 0. This displacement x meters from p, of p from the origin is given by that formula. Find the times when p is instantaneously at rest. This is a really nice 5 marks. So something is instantaneously at rest when its velocity is equal to 0. So what we need to do is just simply expand the formula. So t squared times, so just basically expand the brackets rather, and then differentiate. Okay, so because when you differentiate an expression for displacement, you get an expression for velocity because v is equal to dx by dt. So for the first part of the question, we just needed simply to differentiate. Then we need to recognize that something is at rest when its velocity is 0. So we set that differentiated expression equal to 0, and then we solve. So setting that equal to 0, we can take out a factor of t. We can use our calculators to reverse engineer this factorising, or we can do it by inspection. And what do I mean by using the calculator to reverse engineer the factorising? Well, what I mean is if you take your calculator and you go to xy equals 0 and you put in polynomial degree 2 and you put the quadratic in there. So we have 2 minus 3 plus 1 minus 3 plus 1. So we've got the quadratic programmed in, and we can see that the solutions are 1.5. So what you do to reverse engineer the brackets, you write down t equals 1 and t equals 1/2, and then you just rearrange those brackets to make them equal 0. So let me show you what I mean with this first one. So you would just write down t equals 1/2. You would then say I'm going to times by 2. So 2t equals 1 and take 1 off both sides. So 2t minus 1 must be one of the brackets. And then the other bracket, where you get t equals 1, you just take 1 off both sides. So t minus 1 is the other bracket. So that's just like a nice little technique, because if you're reverse engineering the brackets like that, as long as the examiner can see that you've got the brackets, they have to give you the marks, because you could have just done that by inspection. Okay, so it's a nice little cheat reverse engineering method for factorising quadratics. And we may as well, because we have our calculators. So that's part A done, a super nice 5 marks there. The 3 times when it's at rest are t equals 0, t equals 1/2, and t equals 1. Now, this next bit is only worth 3 marks, but in my opinion, this quite often happens in papers actually. We had a nice, easy kind of like 5 marks, but this part B is, I think, significantly trickier. And, you know, it's surprising that it's worth less marks. Now, the part B says find the total distance travelled by P in the interval from 0 to 2. Now, I think the key point of understanding and the key way to understand this particular part of the question is to be able to visualize what this graph actually looks like. Okay, so here's the formula for our displacement x, and you'll notice that this is a square. This can be factorized rather into a perfect square. It can be factorized into t minus 1 all squared. So actually the formula for x can be written as 1/2 t squared times t minus 1 all squared. So let's now draw the graph of what the displacement of the particle p looks like. Well, we know from our work on sketching quartics that we can say we've got 2 turning points at t squared and t minus 1 squared, both of which are tangents to, in this case, what's called the t-axis. So we can see here at the origin and here at t equals 1, these 2 points are tangents to the curve. Now, being able to visualize that curve is the absolute key to solving this question, because now let's have a think about what's happening. It says the distance traveled, the total distance traveled in the first 2 seconds. So what happens is the particle starts from rest, sets off, gets to some distance here, stops instantaneously, reverses direction, travels back, okay, so it gets to 0 displacement at this point, then changes direction again here, and then moves back out, okay? So the total displacement at 2 seconds would just be this distance here. But the total distance traveled is it's gone out up to that turning point, it's then come back from that turning point to the origin, and then it's gone out again. So the total distance that the particle has traveled is that distance out, that distance back, and then that distance out again. And you can see just how helpful it is being able to have a graph representing that journey. So what we need to do is we need to find out, okay, what is the displacement value at this value here, which we found was t is equal to 1/2, because this is one of the turning points, was when t is 1/2. Turning points were at 0, 1/2, and 1. 0, 1/2, and 1. So let's do that now. So when t is 1/2, we're going to sub into the original non-differentiated equation for displacement, and that gives us 1/2 times by 1/2 squared times by 1/2 minus 1 all squared, which is 1/2 times 1/4 times 1/4, which is 1/32. Okay, so we've got this sus now because we know that what happens is it goes 1/32 out, 1/32 back. So now we just need to find out how far has it traveled here at 2 seconds. So let's sub in t equals 2 in order to calculate that. So when t is equal to 2, we have 2 squared times 2 minus 1. So it's going to be 1/2 times by 4 times by 1, which is 2. So therefore, the total distance traveled is 1/32 add 1/32 add 2, which is 2/16, or 2.06 if you're choosing to write that as a decimal. Again, only worth 3 marks, much less than part A, but in my opinion, substantially more challenging in terms of comprehending and visualizing what's happening there. And I think that those 3 marks for part B would be far, far harder to get. So important that we know how to get those. And then finally, part C, what does it say? Show that P will never move along the negative x-axis. In other words, we've got to demonstrate that we understand that the curve is never going to go down here like this in the negative x. Well, we do that just by factorising it like we did to help us with part B. So we recognise that when we factorise this, it's basically 1/2 times a perfect square. And we can just say that t squared is always going to be greater than or equal to 0. T minus 1 squared is always going to be greater than or equal to 0. 1/2, by definition, is greater than 0. So therefore, the whole expression for x can never be negative, because none of the 3 individual components can ever be negative. And that is how we can see that that is the case. Well, I thought that's a really important question, especially that part B. A very useful illustration of the kind of thing that's popular in this variable acceleration topic. I hope that you found that helpful, and I will see you in the next video.